Hello everyone, and thanks for joining us today. My name is Martin Koppehill. I will be presenting our paper CuART, a scalable Radix Tree lookup engine. So first of all, why did we do this? Nowadays, database sizes are only ever increasing. And the same goes for the query requirements of our users. We do want to provide deeper insights into larger datasets, and that leads to not only new query types or increased complexity in existing queries, but also new database organization. For example, key value stores, distributed databases, NoSQL databases, or column store-based databases. In all of these cases, we need to quickly locate sets of specific entries or single specific entries, which is performed by database index structures. The index structure basically is a mapping from a key to a memory location, which means roughly give me the memory location for a specific entry where the data to this entry is stored. The index structure performance is one of the key factors to the whole DBMS performance because it's consulted for almost every query, and almost every query even consults the index structure multiple to several times. We have different structures that are used today, for example, search trees like the B+ tree, hash tables, prefix trees, which we will talk about now. And recently there has been a rise of learned index structures, which is the application of machine learning to the indexing problems. As every index structure has pros and cons, they are used for different purposes. Prefix trees are not really widely used in production today, although they have some interesting properties. Compared to a B tree or a hash table, those are comparably small and can serve a broad range of query types, for example, range and approximate queries. A significant drawback of prefix trees is that exact queries are pretty slow compared to hash tables, and that is what we wanted to optimize here. As almost every index structure, prefix trees can be implemented very efficiently on modern CPUs because of the super fast caching effects, and they are feasible for massively parallel implementation. In our case, we used ART as a baseline for the works because it's already readily available, and ART itself is a prefix trees with adaptive node sizes. In that case, we have 4 different node sizes for 4, 16, 48, and 256 children. On the right, we have an example of an ART. A to C are different nodes with different sizes. D to G are leaves with different values. And if we now want to run a query for the key bar, then we start at the root node, then we traverse the edge with the key B. We are at the first level, then we traverse the edge with the key A. We are at the second level, go to the edge with the key T, and then we are at the leaf and have found our value. We chose ART as a baseline because it's pretty efficient, and we already have a GPU implementation that is available. In that case, this is GRT. During our testing, we noticed that GRT does not achieve an optimal utilization on modern GPUs, such as the NVIDIA A100 or the RTX 3090. So let's optimize this. We started by analyzing the problems that are inherent to GRT. GRT maps the nodes or the node objects of the ART into a single flat buffer by performing an in-order traversal. When we map the example from the last slide into the GRT buffer, we start at node A, then proceed to node B, then to C, then we have the leaves from node C, and then we have the leaf from node B. That inherently imposes 2 problems. The nodes themselves are represented by aligned union types. That means we have to read the node type first, and then we have to issue another memory transaction for the remaining node. This will become clearer in 2 slides. Another problem is that GRT allows for arbitrarily sized strings, which means that we need to run a slow byte-wise memory access to compare the keys up to a previously unknown length. So what improvements have we done to GRT? First, we folded the upper 3 layers into a singular large node, as inspired by the START paper. Then, we use 1 buffer per node type, as in contrast to 1 buffer for the whole tree in GRT. And to run a complete query, we start at the compact first layers, then we traverse the 4 node buffers, and afterwards we go to the leaf buffer, and if we exit the leaf buffer, then we either have found our object or not found our key we searched for. Another thing we did was to restrict the key length to 32 bytes and delegate longer keys to the CPU because we expected the performance of both of them, like CPU and GPU combined, to be even better than GPU itself. The last thing we did was to implement the look-ahead for the next node type. This is probably the most important point. While GRT requires us to read the header of the node first to get the type of the node and then read the contents, in our case, we have the information which node type comes next into our path we are traversing already before we start reading the node. And that allows us to read the contents in the first memory transaction and save 1 memory bus turnaround time. We did this by implementing a compressed pointer where we have the type encoded into the 8 most significant bits of the 64-bit pointer value and masking these out for the complete memory transaction to read the node. So let's see how those optimizations perform. We have 3 test systems: a notebook with a GTX 1070, a workstation with an RTX 3090, and a server with 2 NVIDIA A100 where we only used 1. The first thing we discovered actually during the test phase of our code, and that is that the same optimizations we performed to the GPU are also applicable to the CPU and deliver some impressive performance results. In this graphic, we can see that the same optimizations applied to the CPU outperform ART by up to 15 times. Then we tested that we made sure that our optimizations are not only feasible for a single GPU, for example, to rule out architectural differences. And we can see that CuART achieves performance improvements over all tested devices, where we measured the most significant improvement on the RTX 3090 because this has the fastest memory block. As a next step, we tested real-world data, in this case from the TPCH dataset, and we can see that CuART outperforms GRT by roughly 20% on average. And also, we did see that the performance gain was significantly less than we expected or we measured in the synthetic test because the TPCH dataset has quite a lot of keys with long shared common prefixes. Then we proceeded to test synthetic data to make sure our optimizations actually work across a wide range of tree parameters. We started by varying the tree size from 64K entries up to 150 million entries, and we see that CuART outperforms GRT on almost every tree size. Another thing that we can see is that CuART's performance is actually rising with a larger tree. We couldn't test more than 150 million entries because then the memory of the GPU was full. So that is a thing we want to improve later. Another thing we did was varying the key length, and while we see that GRT outperforms CuART for short keys, 4 and 8 byte long, anything from 16 byte or even longer keys, CuART outperforms GRT, actually by almost 2 times. And the last thing we tested was the efficiency of the host code, because all of those benchmarks include transfer to and from the GPU. We've seen that the CuART interface is a little bit more efficient on the host side, which means that it will leave up more CPU power for our actual database implementation. The last thing we did was implementing updates. We implemented parallel atomic updates on the GPU. And that is done in 2 stages with 2 sets of data that are shared between these stages. On the left in blue, we have a hash map that is residing on the device. And in green, we have a list of updates to perform. The hash map is filled with the list of thread IDs that are allowed to perform an update. For example, when we have conflicting keys, we only want to have one of the threads to win. In that case, we start at thread 1, and we want to update the key car, so we put the key car and the thread ID 1 into our hash map. Thread 2 and 3 want to update other keys, and thread 4 wants to update car again. So the we calculate the same hash. We go to our hash map and see, oh, there is thread 1 already present. We replace it by thread 4. Thread 5 also wants to update car, so this will replace this key even more, and so on. And then we have a populated hash map of keys to update. In our case, stage 2 then starts to read the entries and the same keys. And our first thread is reading the hash map, sees that the hash map has a different thread ID, and knows that it does not need to perform any update. Thread 2 and 3 have the same thread ID and the same key, so they perform their updates. Thread 4 is superseded again, and thread 5 performs the update. That means we eliminate duplicate updates and therefore reduce the number of memory transactions issued to the global memory. And comparing this to the original implementation leads to severe performance gains. In that case, up to 5x, roughly. We can see that the performance gains are significant for for short keys, because there the memory overhead is even larger. And we can also see that the transaction that for updates, small batches are preferable. That is because our hash map is fixed size, and with the when increasing the tree size and the batch size to update, then we can expect collisions to happen more often, and then the linear probing we use to search for free space to hit. So to wrap up, what did we find? We reduced the number of memory transactions we initiate. We optimized the updates by using atomic transactions. We outperformed both the CPU and the existing GPU implementations over a wide range of GPUs and CPUs. And we found that GDDR6X and HBM2 work best for this. We've also found that the same optimizations are applicable to CPU implementation as well. And in the future, we want to make a few extensions to our project. First, we want to implement structurally modifying operations such as inserts. Then we want to extend this implementation to multiple GPUs, for example, to handle long keys on the second GPU. And the last thing we want to improve is an implementation on HBM-enabled FPGAs, which is currently ongoing. Thanks for your attention, and if there are any questions, I'm here.